And we're actually very fortunate if we go even a little bit further, because were it the case that there wasn't an effective, say, classical description, if you needed to know fundamental quantum mechanics to even start doing science, it's hard to see how we would have made progress at all. We
No,
need to
it's
start,
true.
yeah, with the effective description and then dig deeper and deeper. And thankfully, that's the paradigm and the template that has worked and has gotten us where we are now. So anyway, back to our information paradox story. So now there's some potential non-locality that might be the resolution of how the information of what fell in might somehow be imprinted on this surface, which is where the Hawking radiation emanates from. And so how far can one take that story?
Well, the fundamental problem, of course, is that we had locality for a reason. So if we're going to give up on locality, um, then we have to explain why we don't see it violated all the time. That's the fundamental problem. Hawking would immediately grant us that if there's massive non-locality, then his paradox is no longer a paradox, but then he would immediately come back to us and say, tell me why you haven't seen it already.
Right.
As he should. That's exactly the right thing that he should say to us. And so the main goal of my professional career for the last 10 to 12 years has been to understand how to hide non-locality at the level where you would need it to solve the information paradox. Why we don't see it every time we wake up in the morning, why we don't see it at the Large Hadron Collider,
Right.
where is it? Um,
And so where would you say we are then in telling that story and making it mathematical?
right. So we're still, I mean, as I mentioned at the beginning, right? One of the problems that Hawking had was that he didn't actually have a theory of quantum gravity.
Right.
Um, and so in order to address a question like this, you need to either try to have some general argument based on assumptions that you think a theory of quantum gravity should obey, or you need to have a toy model of quantum gravity. So when I say that we don't have a theory of quantum gravity, I need to be a little bit more careful. What I mean is that we don't have a theory of quantum gravity that's consistent with all the data that we currently have about the world. We do have theories of quantum gravity that are ruled out by experiment. They live in the wrong number of dimensions. They have too much supersymmetry. Um, and
Wrong sign of the cosmological
Wrong
constant.
sign of the cosmological constant. Exactly. Yeah. Issues like this, they don't have the standard model of particle physics. And so the issue is but they do have black holes. And so there's a hope that if we can understand how black holes work in these unrealistic theories of quantum gravity, then maybe that will also be how they work in whatever ends up being the true theory of quantum gravity in our world. Um, and so I've kind of split my time between, but more on the side of trying to understand models because these solvable, or at least I don't know, solvable, but these sort of statable models of quantum gravity, because you need to have something that you can sink your teeth into.
Yeah.
That's one of the, as we were discussing before, it's a very hard problem, and you have to be able to start somewhere. And so, as you mentioned, the natural place to start here is quantum gravity with a negative cosmological constant. Uh, and it's not because I love negative cosmological constant. I mean, after all, as far as we can tell, in our world we have a positive cosmological constant. So it's kind of
Driving the
embarrassing.
accelerated expansion.
Yeah, that drives the accelerated expansion of the universe. If you have a negative cosmological constant, it's kind of the opposite. It's I have um, a baseball or something, and I throw it away from me. And if the cosmological constant is positive, it just sort of accelerates away from me. It falls through the cosmological horizon, and I never see it again. But if the cosmological constant is negative, then what happens is I see it turn around, and after some finite time, it comes back to me with just the same speed it had when I threw it.
Right.
Um, And so it's like living inside of a can where whatever you throw away from you, it comes back in finite time.
Yeah, it hits the
Um,
boundary in some sense and comes
it
back
hits the
to you.
boundary and comes back. That's right.
Right.
Um, and so that's very convenient because it kind of puts a limit on how crazy gravity can be. You know, it's kind of nicely contained in a box. And if you kind of get too excited in what you're doing, then, since you're in a box, whatever you did just kind of bounces off the wall and collapses to make a big black hole. And then just, if you do more stuff, it just gets bigger and bigger. But there's kind of a limit to how weird it can get.
Right.
Um, and so the idea is that in this setting of a negative cosmological constant, um, we understand quantum gravity better, and we can try to understand the emergence of space-time there.
Yeah.
And I want to emphasize that this is not just some hypothetical thing that we understand better. We have like actual concrete theories of quantum gravity with a negative cosmological constant that come to us from string theory.
Yeah.
Uh,
And Juan
where
Maldacena, perhaps is worth mentioning, played a
Yeah, yeah. So the
pivotal role.
best,
Yeah.
that's right. So this is called the ADS CFT correspondence, invented by Juan Maldacena from the Institute for Advanced Study in Princeton. Um, so let me just say what the acronym is, since I don't like using acronyms without
Sure.
defining them.
Please.
So the solution of the cosmological constant of general relativity with a positive cosmological constant is called de Sitter space. De Sitter is a person. That's the person who wrote down the solution. This is the exponential expansion of the universe, that solution. With a negative cosmological constant, the solution is called anti-de Sitter because it's the opposite of de Sitter, and so that's ADS. Um, so then the acronym is ADS/CFT. CFT stands for conformal field theory, which is almost quantum field theory, which we were discussing before. It's the theory of independent degrees of freedom at each point in space to make special relativity and quantum mechanics compatible. Conformal field theory just means it has an extra special symmetry that most quantum field theories don't have, which is scaling symmetry. It looks the same whether you look at it at 5 meters or at 10 meters or at 100 meters. Just everything all the laws of physics are independent of how big things are. So that's certainly not
You
true.
preserve all angles, but sizes can be rescaled.
Yeah, sizes can be rescaled. That's
Yeah.
right. And so that's very different from our world, to be clear, right? In our world, for example, an electron has a mass, and that sets some particular energy scale, and you can't just make everybody 10 times bigger because you can't change the electron mass. And so then all our chemistry would get messed up if you tried to make us 10 times bigger. But some quantum field theories have this scaling symmetry. Those are called conformal field theories. And what Maldacena proposed back in the late 90s is that quantum gravity with a negative cosmological constant, so in anti-de Sitter space, has a holographic description which lives at the boundary of this can that we were talking about. And this goes back to this work of 't Hooft and Susskind, right, who said that the fundamental degrees of freedom of quantum gravity should live at the spatial boundary. And so here in ADS, that's very explicit because, you can think of it like a can of soup. So, we're living in the soup, right, in the center. We throw things out, they bounce off the metal wall of the can and come back to us. Um, and so, we think we're living in the soup, but really, the fundamental description of the system is just living in the metal can. And in fact, it's just a quantum field theory, which okay, we still don't understand quantum field theory perfectly well, but we understand it much better than we understand quantum gravity. So it's saying that this mysterious thing, quantum gravity with black holes and the information problem and everything, is just equal to good old quantum field theory living at the boundary.
And a key thing there is that this boundary theory itself does not have gravity. So it's not
Mhm.
quantum gravity in terms of quantum gravity. It's
Exactly.
quantum
So
gravity in the soup being described in terms of a non-gravitational quantum conformal theory on the tin can, the boundary of the soup. And just so the audience completely understands, this means that any process that happens in the soup, in the interior, has an equally valid but distinct description in terms of processes that happen on the boundary on the can.
right. No, that's exactly right. And so the way that I like to say that is that in ADS CFT, the gravitational spacetime is emergent. Because if you look at the fundamental description of the system, it's just this quantum field theory in the can. There's no geometry of space-time. There's no independent degrees of freedom at different points behind the black hole horizon. It's all just these boundary degrees of freedom. And so it's sort of radically non-local from the point of view of the gravity theory. And this is why it may teach us about the non-locality which is needed to solve Hawking's problem. It seems like even more non-locality, right? Just everything is at the boundary.
Yeah.
And so as soon as we say that, you know, we see the path forward, right? The path is to understand the emergence of space-time in ADS-CFT well enough that we can port it over to Hawking's problem and see what it tells us. And so that's what I've spent the last 10 years doing.
Yeah.